In this video, we're going to talk about one of the more exciting capabilities of NEI's STEM EBIC system, and that's the ability to map conductivity at high resolution with SEEBIC. So for standard EBIC, in order to obtain any EBIC contrast, you need to have two separate paths to ground, and that's because for every electron you measure in your EBIC amplifier, the corresponding hole has to reach ground through a separate path, or else those two charges will recombine, cancel, and you'll have no net EBIC current. SEEBIC, on the other hand, is possible with just one connection to ground, and that's because when the secondary electron that produces the hole leaves the sample, that hole is no longer in any danger of recombining with that electron. So any number of holes can reach ground through this single path and produce a positive current. So while only one connection is required, we can connect multiple connections to ground to a device, and then we get something that we refer to as differential SEEBIC contrast. And the idea here is if there are multiple ways for these holes to get to ground, they will preferentially choose paths to ground that are easier. And this is where SEEBIC starts to give us an idea of the conductive landscape of our sample. So here's perhaps the most simple SEEBIC device you can imagine. It's a metal electrode sitting on an electron transparent membrane. And this is the case where we have only one path to ground. And this effectively generates a secondary electron image of this electrode. Here we have perhaps the second simplest device for SEEBIC we can imagine, which is two electrodes on an electron transparent membrane. And so here we can independently connect to each of these electrodes, and you'll see that whichever electrode we're connected to shows up as bright. And because these electrodes are very well isolated, we get kind of a binary indication of which electrode we're connected to. But moving forward, we can look at devices where things aren't so well separated and see more complicated contrast. So this here is something that's topologically similar to the devices we saw on the last slide, where we have nickel electrodes that are separated by a layer of barium titanate, which is in this case polycrystalline. So we have metal, insulator, and metal separated. This is extracted from a commercial capacitor, and we're going to be measuring EBIC by connecting our amplifier to the nickel electrode on the left, just outside the field of view. So instead of seeing this nice kind of binary separation between the electrodes, when we perform EBIC on this device, we see this very interesting stepwise contrast as we move from left to right on the device. And what's happening here is the holes that are being created in this device are preferentially reaching ground either through the left or the right, where we're measuring EBIC on the left and we're not measuring that EBIC when they leave on the right. And if we do a little math and model this as a current divider, this map can basically be recast as a map of resistance, where at each pixel we get a value for the resistance to the electrode on the right. And so we can basically quantitatively map resistance using this differential SEEBIC contrast. In this case, the stepwise decrease in contrast is being caused by variation in the resistance at some of the barium titanate grain boundaries in this polycrystalline film. So here we're going to look at some resistive memory devices, which are nanoscale. And these are platinum and titanium electrodes separated by about 10 nanometers of hafnium oxide. And here we're applying a bias to the titanium electrode while we're grounding the platinum through our current amplifier. And we're trying to change the resistive state of these devices. So we don't see any indication of changes with increased bias in the ADF STEM images. However, the case is different with the EBIC signal. So to start, we have, similar to the case before, the electrode that we're connected to is showing up as bright because these electrodes are very well separated. However, as we increase the bias, we see that a bright region growing out of the platinum electrode towards the titanium. And so this is a conductive filament growing from the platinum towards the titanium under bias. Up to this point, all the contrast we're seeing is caused by SEEBIC, but as we increase the bias further, this conducting region approaches very close to the biased titanium electrode, and we get a very large electric field. And this is indicated by this bright patch of standard EBIC right here. So This is all contrast that it provides a very rich detail about what's going on in these devices on the nanoscale. And there really is just absolutely no other way to obtain this type of contrast with normal STEM imaging. So we think this is a very promising capability and applicable to any number of situations where you care about local conductivity changes in electronic devices. If you'd like some more information on STEM EBIC, please see any of these sources here. And as always, if you have any questions about our STEM EBIC system or STEM EBIC in general, please don't hesitate to send us an email.